now back again to this performance question. So most of the time, you don't really need performance. There are some examples where you absolutely, absolutely do, right? And sometimes you need it so much that supercomputers are essentially useless. So now I'll tell you, I'll give you one example of this. Suppose you want to solve an ordinary differential equation and you have to take billions of time steps. Well, the blue gene isn't going to solve that problem, right? You'll need a very specific computer design to do that specific task, and we can talk about that later. But most often, the problem that you're trying to do is some very large problem, which, mostly most applications that go for supercomputing are, in some sense, looking at large problems, i.e., you use a lot of memory. And so you essentially just want an acceptable time to solution. You don't want to be embarrassed. You want to run the problem in a few days, good enough. If it takes months, OK, that's bad. So if you look at most of the performance metrics for large-scale codes that run on supercomputing centers, they actually get only a very small fraction of peak. So 5% is not atypical. So therefore, it's fine to not have to push the performance barrier because, like I said, you may not necessarily need it. And there are other sort of compromises you might want to choose, like having a code that's easier to write, easier to read, easier to maintain. And sometimes when you push for performance too much, as I said, you may not need it, and you just end up writing code that's not so easy to use. So that's the first question. And we'll step through, as I step through the example, you'll kind of see like where these decisions are made. So the very first step in the performance portability thing is know what you want. So, and if your performance is a priority, and like I said, it may not be, then you have to design for it right at the start. You can't just say, oh, I'm just going to write some code and optimize it afterwards. That never works. You'll just have to start all over again, and you'll waste a lot of time and you'll get frustrated. So it's extremely important to make sure that what you're doing from the very start is performance oriented. So in order to do that, if you're trying to solve a science problem, you must understand the science. This is a crucial issue, right, that software people never understand properly, is that the set of algorithms that you need to use sometimes, you really have to deeply understand the science you're doing. It's not all matrix multiplies, okay? And if it is, okay, then you can hand it over to a library and get another job, right? But the important thing is you really have to understand what the science is. And there's no replacement for domain knowledge. Because often what happens is, none of the problems that we solve are, in some sense, exact, right? So let me give you an example. So suppose you're solving some PDE. You say, well, I want the answer to double precision or whatever. But the PDE may be answering the science problem only at the 5% level. So what's the point, right? So every time you do something, you must ask yourself, why exactly am I doing this method or that method? Am I really after an answer accurate to parts per million? What's all this about? So only once you have this big picture in mind are you actually going to make the right decisions for performance, right? Portability is another matter. So this is kind of important. The second thing that's important is there's a famous factor of 2 rule, which I don't know how much people emphasize, but I sort of emphasize this a lot, is that there's not really much point in worrying about a loss factor of 2 in performance. Because anyway, the computers are going to be a factor of 2 faster next year, so why waste your time? I mean, I often read papers that are pages and pages long, full of tedious junk, and they end up speeding something by 15%. It's a total waste of time, not worth it. So until and unless you can get at least a factor of 2, and maybe the factor of 2 isn't worth it because what's the difference between 1 hour and 2 hour maybe if you're running a code only once a week, right? So think about it, but at least performance gains should be thought of as powers of 2. So the other important thing is that obtaining performance is not trivial, right? You don't just wake up one day and say, oh, I figured out how to go a factor of few faster. That's not how it works. It involves a fair amount of time and effort. It's usually fairly painful, actually. Sometimes it amounts to saying, I have to throw away everything I did for the last few months and do something completely different. Therefore, if you're going to do this, you don't want to do it too often. So designing for the future is essential. You have to make sure you know what elements, software as well as hardware, you can rely on, what will actually exist in the future, right? And what can disappear. And this, I think, is very important. So one thing that Jeff mentioned earlier is libraries and relying on libraries and relying on other software products. So when you do that, you have to make sure that they will actually exist next year. So this has been something that has bothered me since I started parallel programming in the early 90s. And the number of products that were sold to us scientists as this is the next best thing. If you don't use it, you're an idiot. And most of them have disappeared, right? So be very, very careful about what you actually use. Many things also change under you, and you don't understand, why they changed, what happened. You have no control over it. So, and many things can break. And again, if you have no control over it, it's very hard to tell what happened. So one of the general lessons from experience is the more parameters you can control, the better it is. Now, that's not to say that you should be totally anal and write everything in binary, right? But it just means that you have to have a clear idea of what you're trying to do. The other thing that's important is HPC systems are not your laptop, right? HPC systems are very annoying. They basically don't work. So try to do the simplest possible thing you can on them, and that's a very crucial lesson, right? And they're not like, oh, yeah, I'll download this, download that, run this thing, mash the whole thing together, it'll work. Yeah, that works on workstations, but it usually does not work on high-performance computing platforms. So you have to learn from experience, and I think there's not much more I can say, but that's generally the thing. The other advice about performance is that there's a whole slew of things that you have to think about. But one of the very important lessons, which is not emphasized enough sometimes, in my opinion, is that on-chip/node optimization must come first. So the important thing is that all machines that we work on are lousy, right? This is very important to keep in mind because you have a lot of compute, but the compute to communication balance and memory access is terrible. These machines are completely out of whack, right? So you just can't write some basic code and expect to get good performance. So one thing I would say is if you've written a code, you think it's high performance, and MPI is limiting you, you have done a terrible job, right? Because you failed to take into account this imbalance that exists in these machines. So you must be compute bound. And in order to be compute bound, takes a lot of work. And that work is the chip node play. That's where you have to do it, right? So you have to minimize the number of performance hotspots when you design your code. If you have a very large number of places where performance becomes an issue, it's very hard to manage. You're always playing this whack-a-mole game. You get some performance here, oops, now you have to worry about something else. So it's very good when you're designing a code to have a clear picture of where the performance difficulties are going to arise. And this is something point I made earlier, and not have to deal with them afterwards. Data motion has to be avoided. That's kind of obvious. One of the other things that I've found happen is the trees for the forest syndrome. And I think it's also a sort of work avoidance thing. Often what happens is you start saying, well, there's this one piece of code I really want to fix up and make it better and so on. And you spend a huge amount of time doing that when actually you could have spent your time more profitably on something else. And this is related to trying to be too elegant sometimes. So I think Infeld said very nicely that elegance is for tailors. So sometimes brute force works great, don't change it. Don't try to be too elegant, whatever works, stick with that. The other important thing is also think about various strategies to improve performance, like sacrificing memory for speed if you have spare memory lying around. Vectorize everything, fuse mult adds are your friends. If you don't use them, there's something wrong. And the other thing that's very important is when you're running on any particular machine, there are performance gurus who know everything there is to know about that particular machine. So don't try to learn it, especially if you want to be running on multiple machines, because it's too painful. Just find the right person. That's very, very important. And badger them, and get every piece of advice you can get from them. Now, the second thing is on portability. And here I'm also assuming that you're developing, in some sense, new code. But you're not a software developer, really, right? So there's 3 scales of code development, roughly speaking. So one is the individual, where you're allowed to be idiosyncratic. You can have your own personal style. You don't really care if someone sees how horrible looking your code is. It works, that's fine. And the second thing is a small team. And in the small team, everyone has a well-defined role. Usually small teams are made of people who agree with each other that they are experts, right? And they all, as Jeff was pointing out, they all have their roles. They all fit together well. If they don't, then the appropriate people get ejected, and other people come in. And that's a different way of writing code. Then there's a big teams situation and to open source, which is like completely uncontrolled. So much of this is in the realm of software engineering once you get to even the big team to open source stuff. And mostly I'm focusing on the small team situation here. The second issue that comes in when you're building code or writing new code is the compute environments. So by this I mean, what kind of system are you going to be running the code on, and how much of a big computer are you going to be using? Like, is it small scale use of a machine? Is it medium scale, which means like there's a single project, but the hardware on which the project runs is somewhat diverse? Large scale is that maybe the code is being run by multiple projects with very diverse hardware. So when I use this word scale here, I don't mean necessarily how big the problem is. The problem could take up the full machine. I'm talking more about diversity of how many machines you're running it on. What are you trying to solve, one problem or a number of problems? So these are the two things you have to think about when it comes to portability. You have to consider which categories your situation falls into. For example, if you are an individual writing a very multiple project support situation, that's very difficult because you're one person, you have to deal with a lot of these multiple project issues. So you may have to make design choices that are going to be very different than if a big team were to do the same thing, right? So you have to ask yourself, what categories do I fit in and what choices do I have to make? And in this situation, concrete advice, in my opinion, is pretty difficult because situations vary considerably, and it's a good idea to look at what other people are doing and learn from them. And it's important to be ruthless. Whatever doesn't work, often we just sit around and hope, oh, it'll improve. It will not improve. Just throw it away and do something else. So it's important to dump what does not work as fast as you possibly can. Other thing I need to keep repeating always is simplicity is good. Learn from Google. So Google's programming paradigm is based entirely on simplicity and avoidance of non-functional adornments. That's very crucial, right? And the other thing that I mentioned already is design for the future. Software life cycles, as Jeff mentioned, should be long. Should be, but they are often not. Yeah, there are codes that have been around for decades. There have also been codes that have been around for less than a year, even though a lot of man hours were spent on writing them. So that is an example of very bad code design. And so you have to be careful about exactly what you're doing. So once you've decided that this is how I'm going to do this is what the portability criteria are, then you're going to start. Most science project starts with a compact software core that you build everything around. And this core will grow in multiple directions. So it's extremely important to plan this core, right? What are the software elements that go into this core? And I'm going to not give you a lesson on object-oriented versus procedural. This is really up to you. It's a design choice. You should make it. But the important thing is it'll have key elements. And you have to design it in such a way that even if you make mistakes, it's essentially a matter of gluing the key elements together in a different way to completely reconfigure your code. So think, Unix. Think everything should be small modules that can be plugged together, but in such a way that you don't lose too much performance. So the key is to have flexible elements that are combined together, and you can design around them. So often people consider that performance and portability are in opposition, and this is often the case for obvious reasons, but they can be co-aligned. So I'd like to convince you with a HACC example of how they can be co-aligned. So HACC is the Hardware Hybrid Accelerated Cosmology Code Framework, and it's definitely a small team project. Here's our team. And it does very, very large cosmological simulations. And the design imperative for HACC is that it should run at high performance on all supercomputers at full scale. So it's a very non-compromising attitude. And so HACC has achieved the highest performance ever on a BGQ by a science code. It combines a number of algorithms using a mix and match approach, et cetera, et cetera. I'll tell you more about this. But I quickly want to explain why we are doing this. And basically, this is driven by precision cosmology, which is the fact that sky surveys are producing an enormous amount of information. And we need to solve the forward model of how does structure formation form in the universe, and then compare it against the data. And the interesting thing is that even though the amount of telescope glass has not changed over time, what has happened is that the amount of data coming from the sky, which is driven by CCD technology, is following Moore's law. So because the data is increasing at that rate, the computing requirements sort of follow. So the reason why you need a very large computational effort for doing cosmology is that the entire theory of cosmological probes is in fact the code itself, because the problem is highly nonlinear, and it's not something you can do with a pencil and a paper. You can write the equations down, just a few lines, but solving them is very difficult. And so essentially there are two reasons why you need computing. One is to make predictions for what you'll see on the sky, and the other is to create synthetic sky catalogs that you can then train the observational systems on and make sure that the data pipelines in the observational systems are working like they should. So this is actually a very difficult problem because we need to do all of this stuff at very high levels of accuracy. So just to give you an idea of what the equations we are solving are, so this is the Vlasov-Poisson equation with gravity. So those are the equations on the top right. So this is a 6-dimensional PDE. And it has some extremely nasty properties. Essentially what we are solving for is an instability, so which the figure on the right bottom shows. You start with a very smooth initial condition, and then you get a very messy sort of picture, which is what the universe actually looks like. And therefore, you need very high resolution everywhere in your simulation box. Moreover, because the equation is 6-dimensional, you can't just naively solve it as a PDE, right? Because there's just not enough memory in any machine to do that. So you have to use an approximate method, which is the Nbody technique. So now gravity comes with its own problems. There's no shielding, so you have to solve both for short-range and long-range forces at the same time. And because it's a dynamical Monte Carlo technique, you have to be careful about how errors work. So the Nbody problem is sort of one of the most classic problems in supercomputing. The important thing to keep in mind is that you can't just have a direct particle-particle interaction, because we are going to be running systems with, or we are running systems with trillions of particles, so clearly an n-squared approach is hopeless. So there are different approaches that have been followed over time, and what we do is we basically look for how to combine algorithms to get the most performance. So we combine what's called a particle mesh method, which was invented by, initially in computational fluid dynamics at Los Alamos in the 50s, and then transported to plasma physics in the 60s, and then borrowed by a number of other fields since. And then we also use tree codes. Well, and I won't say too much about this because Hal is going to cover this later on. And we actually use a combination of these algorithms. So the other big issue we have to face is that the code has to work for all of these different architectures, all the way from piles of PCs to piles of cell phones to piles of video cards, whatever, right? So I'll try and give you some idea of how we deal with this. But first, I want to give you a view of how big the actual problems you're dealing with, to give you an idea of why we need both performance and portability. So first of all, if you have a big sky survey, you may be looking at something like billions of galaxies. And in an Nbody code, each galaxy you would like to resolve with, say, 1,000 particles or so. So that gives you 1 trillion particles, right? And that gives you something like, if you converted it to memory, that's around 40 terabytes of data. So if you're running this code and you have, say, 100 outputs, that's like 4 petabytes. So you can generate enormous amounts of data very, very quickly. So the first task that we have is, how can we put all of this stuff inside a computer and get good performance? So we are definitely memory bound in this sense. The other problem that we have is, as you saw, we get structure everywhere, so we need very high dynamic range. The dynamic range that we need is about 1,000,000 to 1 everywhere. And so that's actually a major difficulty, because the local overdensity variation in cosmology is also about 1,000,000 to 1, which means that when you put everything together and you say, okay, what do we need? So we need a supercomputer with memory in the petabyte plus class and performance in the 10 petaflop or so class. And unless we have that, we are basically sunk. And the other difficulty is running one simulation does nothing. We have to run many, many simulations, because we're essentially going to run Monte Carlos against data to get the answer. So we need both performance and portability, because we won't be running on one machine. We'll be running on whatever machines we can get our hands on. So here's an example of a simulation. This is the world's biggest cosmology simulation. It's currently running on Mira. And this is a very, very small piece of it, 50 megaparsec. And you can see how structure evolves over time. And you can see how there's structure everywhere. So I just want to give you this feeling so you understand how the code actually works. And so what happens is you have a smooth initial condition, and then this voids and filaments and clumps form. And now this gives you an idea of the scale of this thing. So this was a very, very tiny piece. This was actually one processor out of 250,000 processors that are used in running the simulation. And so that box that you're seeing on the right is that tiny piece of the actual simulation. And this is now a fly through to the simulation box. So you can see that it's a complex situation, right? There's structure at all scales everywhere, and high accuracy is needed in tracking this. So that's what HACC is basically designed to do. And this is just to give you an example of how well it works. It's basically it runs at something like almost 70% of peak on the blue gene queues. The actual force kernel runs at around 80% plus. And on Titan, the performance is actually better than on Mira, because, well, we can use the GPUs. And we have almost perfect weak scaling. So let's see. I want to finish up in the next few minutes. So I won't tell you too much more about the performance numbers, but they're really, really good. So one of the important things I want to mention, again, this is a general statement about co-design. is that there's a bunch of high-performance computing myths, like don't worry, there'll be compilers that will solve your problem, there'll be a domain-specific language, there'll be special-purpose hardware. Well, none of these things will actually happen. So what is more important is to worry about what you actually have and deal with it. So HACC was originally built to deal with Roadrunner, which was the first machine that broke the petaflop barrier, which was basically an accelerated architecture. And if you just bring it forward some years in the future, you get Titan, roughly speaking. Except instead of GPUs, we had the cell. The cell is more, in some sense, like a mic, but it's not really. In any case, so here are the design principles that drive HACC, right? So one of the important things is that we have to kind of think about all the different machines the code runs on and do it in such a way that it's relatively portable. So we decided that the way to do this is to support a universal top layer, which kind of works on all machines in exactly the same way. And this is an MPI infrastructure, which uses a spectral solver. And the idea was that what we would do is that whenever we switched machines, there would be a short-range force solver that would be machine or architecture dependent, and we should be able to just plug it out and plug in the appropriate one for that particular machine. And this particular local solver should be then optimized purely at the node level for that particular architecture. You never have to worry about the MPI overstructure itself. So that's basically the idea. Our general approach was that we wanted to do everything by ourselves as much as possible. Of course, not to the extent of being silly, but trying to reduce the external dependencies as much as we could. And part of the reason for this is that our code and our team, we often have to deal with new supercomputers that are just on the floor. And like I said, mostly they're broken. So the other libraries that you might want to use if you're a more sane person may not be available to you, right? So that being the case, we have to kind of think ahead and have only the basic stuff that's available. That's the stuff that we use. So the idea is that actually Hal will tell you more about the spectral mesh solver, so I won't say too much here. But so these are technical details about how the code works. Maybe I want to go. I want to stress one or two things about this actually. So basically what happens is in these Nbody codes, you can actually split the short-range solver and the long-range solver, right? And that's what we do. The long-range solver runs in exactly the same way across all architectures, but not the short-range solver. That's different. But the important thing is that the handover between the short-range solver and the long-range solver is kind of important. You want the handover to happen at as small a scale as possible. The reason is that the shape of the force for the short-range solver is subtle and it's not easy to sort of say what it is. So in fact, the shape of the force is given by this bottom equation, the one with all the special functions. So if you actually had to evaluate all those special functions, you would be very, very slow. But if you have a very small range over which you actually where you need this expression, then you can replace it by a polynomial. And if you can replace it by a low-order polynomial, you can actually compute that very, very fast with FMAs. So there are choices of this kind that you have to make, right? The other things that we do is we use a lot of spectral stuff, particularly using the power of fast Fourier transforms. And this is something that might appear non-intuitive because one of the things that people often say is that, oh, as machines get bigger and bigger, spectral methods are going to be harder and harder to do. But this is actually not the case. So if you're clever, you can actually use spectral methods very effectively. And people can talk to me more about this. So we have our own parallel FFT that actually implements all this stuff. So the other important thing that we have is something that we call particle overloading. And this is actually kind of important for two reasons. And so what we do is we basically split the calculation in such a way across the processor, across nodes, if you like, that we try to minimize the internodal communication as much as possible. And we do it by taking a memory hit, by just actually having nodes, in some sense, over-calculate, okay? Because to first order calculation, compute is free. So you can just over-compute to compensate for moving data around, right? So that's one reason. The second reason is that this allows us to make the short-range solver completely local. So it actually doesn't do any communication. That's something that's taken care of by the overall communication framework.